Hi, we are Adib Islam, Victor Internal, and Chongjae Lee from Team 4. This is our final project presentation on Dreamer. Starting off with the paper overview, Dreamer is a model-based reinforcement learning algorithm that learns a world model from images and learns a control policy to interact with the world. The world model enables Dreamer to predict or imagine how the world, i.e. the environment, evolves conditioned upon the action of the agent. Having learned a world model, the agent can predict or imagine the effect of its action in latent space, and learn a policy network by backpropagating the rewards obtained in imagination. While the original Dreamer paper was applied for 2D and later 3D video game tasks, work were also done to implement Dreamer for robotics tasks. Some related works. Planet was the predecessor of Dreamer, where they used similar world modeling with model predictive control to plan in latent space and find the optimal control action. However, they found MPC to be computationally expensive. Dreamer v2 succeeded Dreamer v1 and changed the latent space from Gaussian latent to discrete categorical latent, letting the world model to reason in terms of discrete concepts for accurate prediction. Daydreamer implemented Dreamer v2 in the robotics domain, learning complex behaviors such as quadrupeds walking gait in an hour using only the agent interacting directly in the world without a simulator. Dreamer v3 improves Dreamer v2 by stabilizing the learning by using techniques like normalization, balancing, etc. Dreamer v3 is very robust and can solve various tasks without hyperparameter tuning. Here's our proposed improvement for Dreamer. We identified some limitations of the Dreamer algorithm and focused on a few of them to improve on. Learning an imperfect world model during early learning stage can result in improper planning and policy. Thus, the samples collected will be limited to the poor interactions in the environment. Therefore, the agent gets stuck in a locally optimal solution. This becomes an issue when we want to learn a hard task such as running in the humanoid benchmark environment. Thus, we plan to implement curriculum learning to train the agent on easy tasks first and then gradually train on harder tasks. We also identified that the gated recurrence unit used in Dreamer for world modeling can lead to long-term memory loss. Thus, we decided to replace the GRU cell used for modeling with the Mamba architecture. We believe that this will enable us to solve complex tasks that requires long-term planning. Our goal with this project is to accelerate learning of new tasks for a humanoid robot by leveraging knowledge from previous tasks through curriculum learning. Furthermore, we hypothesized that replacing the GRU cell in Dreamer with Mamba would lead to enhanced long horizon planning. Here's how we implemented our project. We built on top of the open source implementation of Dreamer v3. We aim to solve humanoid robot tasks using Dreamer. To achieve this, we utilize the humanoid benchmark, a simulation environment designed for whole body humanoid locomotion and manipulation tasks. We incorporated our improvements into Dreamer v3 and evaluated its performance in this environment. While Humanoid Bench includes 27 diverse tasks and various observation spaces, including egocentric visual observations, we focused only on 4 specific tasks: stand, walk, maze, and run, and used an observation space comprising the humanoid robot's joint angle position and joint velocities due to simplicity and time constraints.
So now let's talk about the methodology part of our project and more precisely the integration of curriculum learning. So as we explained in the previous presentation, this technique is implemented to enable better convergence by avoiding local experiments. One reason why the model is slow and may fall into local optimum is that the model is trained independently for each task and from scratch. Integrating curriculum learning allows tasks to be run sequentially, reusing learning experience from previous tasks. We also started working on the curriculum learning training pipeline, and we realized that we need to decide on the measure of difficulty. We decided that it shouldn't be something arbitrary like our intuition. Instead, it should be based on the reward obtained from the task. However, different tasks have different scale of reward, making it hard to naively use the reward environments to design the curriculum without any processing. To respond to this challenge, we took inspiration from the paper on the power of curriculum learning in training deep networks. In the last presentation, we evaluated the difficulty of 29 tasks available in the simulation thanks to a benchmark. These tasks can be, for example, walking, sitting, or throwing an object. The evaluation is based on the reward curve obtained over 1,000 training iterations. To achieve this, we use 3 different metrics that we presented last time. These metrics are based with the same principle. The more iterations a model requires to learn a task, the more complicated the task is. A difficulty ranking is calculated for each metric, followed by an overall ranking. This ranking determines the order of which tasks are learned. The simplest task will be learned first, and the most complex task at the end.
An issue we quickly stumbled upon was how long do we train a single task for and when to move on to training a new task. We initially considered using normalized scores for evaluating task performance. However, since the maximum return fluctuates during training, normalized scores were deemed unsuitable. While a more sophisticated task completion criteria would have been ideal, for simplicity we analyzed the offline training logs for each task without curriculum learning to understand the reward curve behavior. Based on this analysis, we selected a return threshold just before the reward curve plateaued. To determine task completion during training, we computed the average return of the last 10 evaluations for a given task. If this average exceeded the predefined threshold, we considered the task complete, stopped training on it, and progress on to the next task. We also believe there is a good chance that the model forgets previously learned tasks when it starts training on a new task. To address that, we added task labels to condition the model learning on the task. The original observation space only had the robot's joint angles and joint velocities. For each task, we created a one-hot encoded label and added that to the specific task label, thereby associating each task label with its desired behavior during training. This prevents catastrophic forgetting as the model doesn't overwrite knowledge from one task, for example, stand, when it learns another task like walk.
Let's talk about Mamba. The GRUs in Dreamers understand struggle with long-term dependency due to limited state size. Inspired by a study comparing transformer and LLMs, we considered using a transformer. While previous work applied transformers mainly to other actors and critics, our focus is on modeling the entire environment. We gained insights into parallelizing input from these studies, but transformer proved too memory heavy. Instead, we adopted Mamba, which handled long-term dependency via a selective state space mechanism with less memory. We replaced the Dreamer's original RSSM with the Mamba model. The left is the original RSS structure, and on the right is Mamba Dreamer. Dreamer's world model consists of six components. The deterministic state model learns temporal dependency of state transitions and embedded the current state effectively. In RSSM, previous state must be continuously accumulated. In our Mamba-based structure, however, all inputs are fed in parallel, eliminating the need for HT-1. This prevents the diminishing influence of distinct past states and ensures effective long-term memory retention by considering all states simultaneously. Representation models that infer stochastic states from observations were originally embedded with accumulated information about previous states, but our model break this link. This is because our states are considered composite in Mamba's model anyway. This should allow for faster computation since there is no dependency. Next, we changed the policy. We started passing in the previous state and allows the data from all states to be input. For training, RSSM used a loss function that approximated the posterior probability. In contrast, our new model compute each latent state ZT solely based on the current observation XT without directly taking into account previous latent states or past observations. In the original Dreamer, we store observations and actions step by step in the replay buffer. However, our model needs our state. Therefore, we create a new environment-specific replay buffer that accumulated the entire episode as shown in the code on the right, and sequentially fed the previously collected episodes into the police to generate the next data segment. We continuously accumulate our state from the start, embedding them without relying on previous states. This method is memory intensive, making it challenging to imagine every possibility, as LSFM does. To address this, we randomly selected a subset K of the full sequence length for imagination. Also, we wanted to fairly compare Mamba to RSSM by using the Mamba model of similar size, as shown on the right. The actor and critic remain unchanged. Mamba is structured in modular blocks, and our model we use for such blocks.
Here's the evaluation and results. In the bottom right plot, we show the return curve for each task without curriculum learning. Notably, each task requires at least 6 to 7 million steps to achieve a reasonably high return. On the bottom left plot, you can see the return curve for our complete curriculum learning approach. and the top left plot illustrates the time steps at which the curriculum transitions between different tasks. With curriculum learning, the number of training steps required to meet the task completion criteria decreases for each subsequent task. Using this approach, we achieve comparable performance on the four tasks: stand, walk, maze, and run in just 11 million steps. In contrast, training these tasks separately without curriculum learning would require approximately 40 million steps, and each of those models could only do that one task. Interestingly, once the robot learns to stand, which takes about 6 million steps, it only requires 2 million additional steps to learn to walk, 200,000 steps to navigate the maze, and 3 million steps to run. This demonstrates the efficiency of leveraging prior task knowledge in curriculum learning.
As mentioned earlier, we achieved good result in curriculum learning, but Mamba didn't get proper learning result. The figure on the left shows the result of implementing a model based on the transformer in our related study, but our Mamba model didn't increase. We felt the need to analyze. We identified four potential large problems. First, the size of model was not large enough. In other related studies using transformer, the model was trained without caring about the size of the model. We analyzed that it may be because the model size was not large enough to learn the task. Secondly, we think that converting various hyperparameters for the existing RSSM to Mamba actually hindered learning. Third, we filled the reply buffer with 32 embodiments because of the difficulty of learning multiple embodiments on our computer. We believe that filling the reply buffer with reply from such a small number of embodiments may have led to overfitting. Finally, we analyzed that the fact that the RSSM only outputs HT to calculate the loss, while Mamba output H12T, and we only used HT to calculate the loss, seems to have caused the problem with the gradient. We put in a lot of effort and succeeded in replacing the old RSSM with Mamba. We think we need to build a more optimized model with further debugging and experiment.
This part, we will talk about the limitations of our project. So the first limitation comes from the definition of difficulty. This notion is relative, so the order of tasks can be modified according to the meaning given to this term. Moreover, there is no absolute truth that can enable us to check if the order of difficulty is right. To continue, these metrics were used on only one training session of the model, so this evaluation can be biased by outlier. Finally, the meaning of this matrix is still ambiguous, since the absolute value means nothing, and they are just used for comparison purposes. A second limitation comes from the fact that we train our different models with predefined and optimized hyperparameters of the original model. However, we carried out modifications on this approach. That's why the original parameters may not be relevant anymore. Adjusting parameters could improve performance, but resources constraints restricted in-depth exploration of these settings. For the last point, we haven't covered all ablation study cases, as the training sessions were long and consumed a lot of resources. That's why we can't be totally sure that merging our two approaches will produce the best results. But this can be easily fixed with more time. Now let's move on the improvement parts. So in this part, we will talk about potential improvements. The first idea is to use the progressive reward shaping. The goal is to divide a task into a succession of subtasks. For example, for handling an object, we can divide it into 3 steps. The first one is grabbing the object, then moving the object, and finally positioning the objects. The point is that the reward varies to adapt to the learning progress. In other words, the reward will focus on a subtask, and then once the subtask has been learned, the reward will change. This idea is highlighted in the paper Accelerating Lifelong Reinforcement Learning via Reshaping Rewards. And finally, as we said in the previous presentation, we also want to confirm the long-term benefits of our proposed application of Mamba in Dreamer. We can do it by integrating more complex tasks, more precisely by testing the model on tasks with long-term dependencies and ordered tasks. A good example consists of placing colored balls in a random order in a square room and touching the balls in a certain order. We can also improve original tasks, like the maze task, but with the introduction of ordered goals to emphasize memory. This concludes our presentations. Thank you.